Somewhere in the early universe, astronomers using the James Webb Space Telescope discovered a black hole that appears to be pushing the limits of everything we thought we understood about black hole growth. This object was found feeding on surrounding matter at more than 40 times the theoretical Eddington limit. Not slightly above it, not twice the expected rate, but more than 40 times faster than the rate normally associated with the physical limit of black hole accretion. And this may not be an isolated case. Webb has revealed an entire population of mysterious objects that appear to contain black holes far more massive than expected for their surrounding galaxies. Some of these black holes seem to be enormously oversized compared with the amount of stars in their host galaxies, raising a fundamental question. How did black holes become so massive so quickly? To understand why this is such a big deal, we first need to understand how black holes normally grow. A black hole forms when an enormous amount of matter collapses into an extremely compact region, creating gravity so powerful that not even light can escape once it crosses the event horizon. Many black holes form when massive stars reach the end of their lives and their cores collapse. Others can grow through mergers with other black holes. Once a black hole exists, another important growth mechanism takes over: accretion. Gas and dust surrounding the black hole spiral inward. As this material becomes compressed and heated, it releases enormous amounts of radiation. That radiation pushes outward against the incoming material. This creates a theoretical limit known as the Eddington limit. The basic idea is simple. If a black hole tries to consume material too quickly, the radiation produced by the infalling matter can become strong enough to push additional material away. In other words, the black hole can begin interfering with its own food supply. For a long time, this limit has been an important part of models describing how rapidly black holes can grow. But Webb has now revealed objects that appear to challenge those expectations. When astronomers observe extremely distant galaxies with Webb, they are effectively looking into the universe's ancient past. The light reaching the telescope has traveled across enormous distances before finally arriving at its mirrors. That allows astronomers to study galaxies and black holes from a period when the universe was still extremely young. One of the most dramatic examples is a black hole known as LID 568. Astronomers combined observations from Webb with NASA's Chandra X-ray Observatory and discovered this low-mass supermassive black hole inside a faint galaxy. What made LID 568 particularly remarkable was its feeding rate. Researchers determined that the black hole was accreting material at more than 40 times the Eddington limit. Scientists believe this extreme feeding episode was probably temporary rather than a permanent condition. But even a short period of hyperaccretion could have enormous consequences. If black holes can occasionally enter such extreme feeding phases, they may be capable of growing far more rapidly than traditional models assume. And LID 568 is not the only strange object Webb has uncovered. Another mysterious population has become one of the biggest surprises in early universe astronomy. Astronomers call them little red dots. These compact, extremely distant objects appear reddish in Webb's observations. At first, researchers were uncertain about their true nature. Were they ordinary galaxies filled with stars? Or were they powered by something much more extreme? As more observations became available, evidence increasingly suggested that many of these objects contain actively feeding black holes. The surprising part is the apparent relationship between the black holes and their host galaxies. In the nearby universe, astronomers have observed a broad relationship between the mass of a galaxy's stars and the mass of its central black hole. But some little red dots appear to violate that relationship dramatically. Their central black holes can be enormously massive compared with the stellar mass of their host galaxies. In some interpretations, the black holes could be hundreds or even thousands of times more massive than expected from the normal relationship between galaxies and their central black holes. That creates another major problem. Perhaps black holes did not simply grow alongside their galaxies. Perhaps, under certain conditions, the black holes grew first and extremely rapidly, while the surrounding galaxies were still struggling to assemble. One particularly interesting example is the object known as Canu LRDZ 8.6. Webb observations revealed evidence for an actively accreting supermassive black hole inside an extremely young galaxy. The black hole appeared disproportionately massive compared with the stars surrounding it. That observation suggests something important. Black holes may have been able to race ahead of galaxy formation rather than simply following the growth of their host galaxies. So how could this happen? Researchers are investigating several possibilities. The first possibility involves the initial seed of the black hole. If black holes began as remnants of massive stars, their initial masses would have been relatively small. They would then have needed to grow rapidly through accretion and mergers. But perhaps some black holes did not begin that way. One proposed explanation is called direct collapse. Instead of forming from the death of a single star, enormous clouds of primordial gas may have collapsed directly into black holes. Under the right conditions, these objects could produce black hole seeds thousands of times more massive than ordinary stellar remnants. That would give the black holes an enormous head start. Instead of beginning with a relatively small seed and trying to grow into a supermassive black hole, they could have started their lives already carrying thousands of solar masses. But direct collapse has its own difficulties. The gas cloud needs very specific conditions. It must collapse without breaking apart into smaller pieces that would eventually become stars. Its chemistry, temperature, and rotation all have to fall within a narrow range. Computer simulations can produce direct collapse black holes under suitable conditions, but creating enough of them to explain the entire population of massive early black holes remains challenging. That is where some of the more exotic ideas enter the discussion. One proposal involves a special form of dark matter known as ultra-self-interacting dark matter. Dark matter is invisible and does not appear to interact with light in the same way ordinary matter does. We infer its presence primarily through its gravitational influence. The proposed self-interacting version would behave differently. A smaller component of the dark matter could potentially interact strongly with itself and become extremely concentrated in the centers of early galactic structures. If such a component exists, it could help create the conditions necessary for unusually massive black hole seeds. The idea is still theoretical, but it demonstrates just how difficult the early black hole problem has become. Scientists are not simply trying to adjust a small number in an existing equation. They are investigating whether our assumptions about black hole seeds, galaxy formation, accretion, mergers, and even dark matter need to be reconsidered. Another possibility is runaway black hole mergers. The early universe was much denser and more chaotic than the environment around most modern galaxies. If black holes frequently encountered one another in these dense regions, repeated mergers could have rapidly built up their masses. Instead of relying entirely on gas accretion, a black hole could gain substantial mass through a sequence of mergers. This could potentially explain some of the unusually massive black holes appearing in Webb observations. There is also evidence that some of the earliest known supermassive black holes were already surprisingly massive when the universe was still extremely young. One such object has been observed with a mass of hundreds of millions of times that of our Sun. That is difficult to reconcile with the simplest versions of conventional black hole growth. A black hole starting from a small stellar remnant would need to grow extraordinarily efficiently to reach such a mass under those conditions. And once again, little red dots appear to be part of the story. When Webb first revealed these strange objects, astronomers debated whether their unusual appearance came primarily from stars or from active black holes.